Hi students, welcome to the discussions on the advanced shield designs. In the previous video, you have seen the design of a shallow bin, a bunker. In today's class, we shall see the design of a deep bin, which is called a silo. Right? Whereas now I wish to show a photograph of a deep bin silo, which we'll try to design in this class. Right now, this is how I'm showing a silo, which is a circular silo, and which is resting on four columns, and this portion is what called the hopper bottom, which is in the form of a truncated cone. Here there is an opening, and also at the top we do have a conical top, right, for protection of the material, right, and also there is an opening at the top so that the material can be dumped from top, and the material can be taken from the bottom. And the bottom we do have the trap door, and generally that bottom opening is in the form of a circular opening, right, and this is supported on four columns, which is resting on a combined footing, right. Now let's see a numerical example of a problem wherein uh, this is how the problem is: design a circular steel silo of internal diameter 4 meters and height 12 meter to store cement of bulk density 15.5 kilonewton per meter cube. Angle of internal friction 23 degrees, and height of hopper bottom 3 meters, and diameter of opening is 0.6 meter. That is how the data is given. Now we need to design. Starting from fundamentals using the IS code and specifications. Right now we'll see here already the size is already given. That internal diameter is 4 meters and the height of cylindrical portion is 12 meter, right. Sometimes what may be given is it may be given that you propose the size of the steel silo to store cement of say 3000 kilonewtons. Then if such data is given, then you divide with the density so that you will get the capacity, how many meter cube of the internal storage is required. Once you know the internal storage, then you try to fix that internal storage, one in the form of cylindrical portion, major portion, right. Two second, this is cylindrical portion. The second part is conical hopper bottom in the form of frustum of cone, right. Here readily the dimensions are given, right. Hence now I'll take those dimensions. Otherwise you need to fix the dimensions if the storing capacity of the material is given like this, right. That here this cement being a powdery material, now I'll note down from the code book IS 4995 what are the coefficients of the pressure coefficients, right. The pressure coefficient during filling is equal to 0.5, and the pressure coefficient during emptying is 0.7, and we can also note down from the same code 4995 that the angle of friction between the material and the wall during filling pi prime is equal to 1 times pi. However, pi is given as a 23 degrees angle of internal friction, hence it is same 23 degrees, and the angle of friction between the material and the wall during emptying pi prime e is equal to pi, which is also equal to 23 degrees. And once we know that, then I can calculate the coefficient of friction during filling, which is tan pi prime f. Therefore, substituting numeric values, will get 0.4663, and during emptying mu e is equal to tan pi prime e, which is also 0.4663. Both are same. Then this is how the geometry what is given, students. The height of the cylindrical portion, right. is 12 meter like this, or this 12 meters. This is a 12 meter, below which there is a conical bottom, right? Then also the hopper portion is a 3 meter deep, 3 meter deep, and what is given is 0.6 meter circular opening, diameter circular opening is there. Hence, if I deduct from this uh, diameter of silo 4 meter, now I'll get 3.4, which is divided into two equal parts, 1.7, 1.7, right? That is how the uh, uh, width width right? Then this height is equal to 3 meters. Then using this data, I'll calculate the hydraulic mean radius, which is defined as the ratio of the area to the perimeter. This being a circular geometry, I do have area pi by 4 d squared divided by pi d. I'll get d by 4, where diameter of this bin or silo is itself is 4 meter. Therefore, 4 by 4 means 1 meter. And the coefficient ZOE, E means during emptying, ZO during emptying, R divided by mu prime E KE. Substituting the above numeric values, I'll get 3.064. And the same during filling, ZOF, R divided by mu prime F KF. However, please note down that KE and KE and KF are quite different, though mu F and mu E are same, right? For substituting, which now you'll get a result 4.289. 4.289. Now I'll calculate H by ZOE. You can check that this H by ZOE during emptying is greater than H by ZOF during filling. And so this indicates that the empty case will govern the design. The empty case will govern the design, not that of the during filling, right? That. Now I'll calculate at a depth of 12 meter, starting from the top. What is H by ZOE? H is 12 meter divided by ZOE. ZOE is equal to 3.064. It works out 3.916, or 1 minus e to power H by ZOE will now work out upon substitution 0.48, 0.48 numeric value. Hence, the horizontal pressure during emptying, given by the formula WR divided by mu prime E 1 minus e to power H by ZOE, where W is the density of the material already given in the problem 15.5 for the cement, and R radius is equal to 2. Radius is equal to 2 because diameter is given as 4 meter divided by 2, and mu prime E we have calculated 0.4663 multiplied by this 1 minus e to power H by ZOE 0.48. Upon calculation, I'll get this result: horizontal pressure during emptying as 32.57 kilonewton per meter square. Then we already know the relation between the horizontal pressure and vertical pressure in the form of the pressure ratio. Therefore, dividing with pressure ratio, now I'll get the vertical pressure during filling is equal to, say, 65.15, right? Then the hoop tension or the bursting force. For calculation of bursting force, I'll calculate hoop tension, which is this intensity of hoop force or hoop stress, 32.57 P D. D is equal to diameter 4, P D by 2. 2 is equal to 2, right? Now substituting, which now I'll get 65.15 kilonewton per meter for the design hoop tension per unit length. So many kilonewtons, right? PD by 2. Now I'll move to the design of cylindrical wall plate. Therefore, I want to design this wall of this cylindrical portion. Now I'm assuming the thickness of this wall as 8 mm. If I cut, I can see the thickness as 8 mm. Then, for assuming that, now I'll get the hoop stress is equal to PD by 2T, right? Already PD by 2 is calculated as 65.15 in the previous heading, divided by thickness 8 mm. Now I'll get 8.143 MPa, Newton per mm square, MPa. Right? This is hoop, means a tensile force, right? which is much less than the permissible axial tensile stress, which is 0.6 Fi. Therefore, okay. Therefore, F. Okay. It will not burst, right? Then I'll also calculate the compressive forces like this, right? The vertical plate is not only subjected to the bursting tensile force, but also major load is because of the storing of the material, which will try to compress the plate, like this, compress the plate, right? Now I'll calculate that. Hence, what is the total vertical load in the cylindrical portion is nothing but the area of this circular part pi by 4d square multiplied by height h multiplied by material stored density, or density of the material stored. It's gamma w. Now substituting numeric values, I'll get pi by 4 multiplied by 4 square 12 multiplied by 15.5. Say 2337.3 kilonewtons is the total vertical load due to weight of the material, storing of the material. Now next, what is the vertical load due to vertical pressure? We already calculated the vertical pressure as 65.15 because this is how vertical pressure during filling, 65.15. I'm just recalling that. Please make a note. And so that multiplied by the area of this circular section, pi by 4d square, where d is equal to 4. Substituting it, now you get say 818.57 kilonewton. Therefore, out of this 23.37.3 total vertical load, the load due to vertical pressure itself is 818. Therefore, the difference of these two is the vertical load on the side plates, on the side wall or side plates, on the side wall or on the side plate. Therefore, is the difference of these two values. The difference now will work out 1518.70, 1518.70 kilonewton is the load. Then now I'll assume the sulfate of the plates, including the stiffeners at the rate of 0.8 kilonewton per meter square, acting on the surface area, right? Because the stiffeners are already provided along the total periphery, of the vertical plate, so that they will avoid bursting as well as the buckling. Hence, that now works out 0.8 kilonewton per meter square multiplied by the surface area pi d multiplied by height 12 meters, or it is 120.6 kilonewton. And also the inside we do paint a protective lining paint, right? Therefore this lining will withstand the wear and tear, because once material is dumped from a particular height, that will hit the walls of the material, and that will undergo abrasion, right? Therefore that will undergo wear and tear. Therefore, in order to avoid that, we will do a protective lining paint, right? Hence its intensity is assumed at the rate of 1.2 kilonewton per meter square. Hence inside volume, I'll calculate pi d multiplied by height. Inside area is surface area is equal to pi d multiplied by height 12, right? That multiplied by 1.2 kilonewton per meter square, or it works out 180.96 kilonewton. And also I'll assume the sulfate of the top cover plate, because I need to provide a cover plate at the top, so that no other unwanted material falls in the bin, right? For which it is intended, right? Therefore, now there is a sulfate of the top cover plate is assumed at the rate of 4 kilonewton per meter square, including the platform, for checking purpose, right? Therefore, this 4 kilonewton per meter square multiplied by area pi by 4 d square, which is equal to 50.26. If I club up everything top to bottom, now it works out, say, a value, right? These summations, right? 1518 plus 1 plus 120.6 plus 180.96 plus 50.26 will work out approximately 1870 kilonewton of the compression load on the wall. That much of huge compression is there, right? On the wall, on the periphery, right? Therefore, now I'll calculate how much of intensity of that compression force per unit length of the periphery of that periphery. Therefore, I'll divide with total peripheral length pi multiplied by d. Doing which now I'll get the intensity of that compression force per unit length is equal to 148.82 kilonewton per meter, right? Then once I get this, already the thickness of the plate is assumed as 8 mm. Therefore, what is that actual compressive stress? Sigma AC cal is equal to the total compressive force per unit length 148.82 Newton per mm or kiloton per meter, both are same, right? Divided by thickness it gives divided by 8, or it gives 18.6 Newton per mm square, or MPa, which is much less than even assuming even the slenderness ratio maybe some 20 or 30, you can check that the permissible axial compressive stress may work out much more than 18.6. Therefore, it is okay. It is okay. Otherwise, the basic value, assuming slenderness ratio lambda is equal to 0, is 0.6 Fi 165. Therefore, okay. Therefore, okay. Right now, therefore this is individual check, it is okay. But in addition to this axial compressive stress of 18.6, which is acting in the vertical direction, also at the bottom there is a hoop tension or bursting force like this, right? Therefore, which is at 90 degrees, which is acting at orthogonal to this 90 degrees. Therefore, assuming Poisson's ratio of the steel material as 0.3, because these are at 90 degrees, hence now I'll get the total compressive force is predominantly the compressive force, the vertical direction plus from the lateral direction due to Poisson's ratio effect, 30%, 0.3 multiplied by tensile stress, the tensile hoop tension, which is 8.143. Therefore, that gives 21.05. You please see this. This is out the hoop stress 8.143. There's a tensile force sigma AT cal. Right? And so there is also recalled. Then the total compressive force is now 21.05, which is much less than the basic value itself is 0.6 Fi 165. Even if you assume slenderness ratio maybe 20 or 30, the permissible value will be in such a case it will be less than 165, but much greater than 21.05. Hence okay. Now we'll also calculate similarly the total tensile stress is a basic tensile stress 8.143, assuming Poisson's ratio 0.3, the compressive force, because it's from the 90 degree direction, right? Hence the total tensile stress, intensity of the tensile force 13.73 Newton per mm square, which is much less than the basic value of 0.6 Fi. Hence okay. 165 MPa Newton per mm square. Hence okay. And this indicates that the proposed 8 mm thickness of the wall is okay from one, taking the compression load point of view as well as the bursting point of view. Hence the 8 mm thickness itself is the final thickness, right? And also you propose ISA 65 by 65 by 6 mm nominal size horizontal stiffeners along the periphery, like this, along the periphery, right? Like this. Once 65 by 65 by 6 in the vertical direction as well as in the horizontal direction, right? Whereas now I'm assuming these stiffeners in the horizontal direction so that the hoop force or bursting force at every level that will be there. Hence horizontal stiffeners, this 165 by 60 this 65 by 65 by 6 mm are provided like this, so that they'll run along the circumference of the silo, right, at every 1.5 meter center to center. I do have a total height of 12 meters, therefore 12 divided by 1.5, I'll get so many number of spacings, 8 number of spacings, right? 8 number of spacings means you provide in total 9 stiffeners, because including top and bottom it will work out 9. Between 9 I do have 8 spacings, right? Now also provide equal number of, say 9 number of vertical stiffeners in a similar fashion, the same ISA 65 by 65 by 6 mm. Now it is spacing of total peripheral length pi d, pi multiplied by 4 divided by 8. Divided by 8. Now it works out 1.57. Now you can see that each panel is approximately a square, 1.5 by 1.57, approximately a square panel, which is curved panel, right? Which is a curved panel like this, right? Which is a curved panel. Hence, that will avoid the bursting. That will avoid the bursting. That is the main purpose, right? That is how the panel in curved space 1.5 by 1.57. Now, once I do that, now I'll move to the analysis and design of hopper bottom portion. Students, I hope you're understanding, right? Then I'll assume the thickness of this hopper bottom portion also as 8 mm. However, this in any case should not be less than 6 mm, which is exposed, if at all that uh, structure is exposed to open environment. Obviously, the bunkers and silos are generally exposed to open environment. Hence, from that the corrosion point of view, the thickness should not be less than 6 mm. But now I'm proposing 8 mm. Right? And we already have calculated the total vertical load due to the vertical pressure in the previous subheading as 818.67 kilonewton. Right? And now I'll calculate what is the weight of the material in the conical hopper bottom portion, means frustrated cone, the frustum of cone, right? There, the volume of the frustum of cone, conical frustum of cone, is 1 by 3 pi r square h. 1 by 3 pi r radius is equal to 2 square multiplied by h, height of that frustum of cone or conical portion or hopper bottom, all are same, is 3 meter, and the density of the material stored 15.5 kilonewton per meter cube. Now it works out 194.78 kilonewtons, and there is a weight of the material in hopper bottom. And assuming the sulfate of the plate and stiffness at the same previous assumption, 0.8 kilonewton per meter square, then I'll get the total surface area of the inside surface area multiplied by this 0.8 kilonewton per meter square. Let us say it is approximately working out 40 kilonewton. And if I club all these, total vertical load plus material stored 194.78 plus 818.67 plus 40, it now works out approximately 1053 kilonewton, 1053 kilonewton in this portion, right? Now here, this is how that height of that hopper bottom 3 meter, and this dimension is 1.7 meter. This is circular opening of diameter 0.6 meter. Hence, now I'll calculate what is that length of this inclined hopper bottom plate, which is in the form of a frustum of cone, right? If I cut a unit strip like this, it seems like this, right? Therefore, its length is equal to square root of 3 square plus 1.7 whole square, or it gives 3.448 meters. Then the longitudinal tension or the intensity of the tensile force. We already calculated this force, total load 1053 approximately. That is acting on a total peripheral length of pi d, pi multiplied by d. This peripheral length pi d, right? Therefore, that here I'm calculating that for this upper bottom portion. Hence, I'll take this ratio 3.448 compared to that of this 3. Hence, now I'll get this result as 96.36 Newton per mm or kilonewton per meter. This is the intensity of the tensile force, right? Hence, the tensile stress, longitudinal tensile stress is equal to that intensity of tensile force, so many Newton per mm, 96.36 divided by thickness 8 mm. It gives 12.04, which is much less than the permissible value of 0.6 Fy, 0.6 Fy, which is 165, Hence, okay. Then Also, we do have horizontal compressive force of 12.04. 12.04 at this top of this uh, inclined upper bottom portion. Hence, its cast component, if I take that, now works out 5.94. 5.94. Hence, even if that I add in the form of tension, right? In the form of tension, even the total tension is 14.1, 14.1 Newton per millimeter. Then also this is much less than the permissible axial tensile stress of 165.6 FI, 0.6 FI, sorry, 150 MPa. Hence, okay. Hence, okay. Hence, similarly, you provide the same ISA 65 by 65 by that 6 mm stiffness along the horizontal direction as well as the sloping portion. What I have already shown in the previous sketch, right? Like this, right? ISA 65 by 65 by 6 horizontally as well as in the sloping portion also, sloping portion. We now shown a figure of this silo in the starting of this discussion, right? Then now we'll move to the analysis and design of a ring beam. The bottom ring beam, which is a circular ring beam, this entire cylindrical portion is resting on a massive ring girder, which is resting on a set of columns, n number of columns. Now, let me calculate what is the total load, what is coming onto the ring beam or ring girder. Here I do have weight of the material stored in the cylindrical portion 2337 kilonewtons, and also in the upper bottom portion approximately 195. Summation of these two is around 2531 kilonewtons. Right? And also the self-weight of the stiffness we already calculated in the previous subheading. I'm just recalling that 120.6 kilonewton, and self-weight of the lining is already calculated in the subheading, previous subheading. I'm recalling 180.96, and the self-weight of the top cover plate also calculated as 50.26, and the hopper stiffness weights including its self-weight is assumed or calculated as 40 kilonewton. Hence, the summation of all these is the total load coming onto the ring beam, which is 2972 kilonewton, or around approximately 3000 kilonewton. Now, assuming the ring beam supported on eight number of columns. Now I'll take from IS 4995 what are the coefficients for the bending moments at the support as well as the torsional coefficients. The coefficient for the bending moment, negative bending moment or support bending moment is 0.00827. That is a K negative, right? Therefore, the bending moment at the support M KWR, K is equal to 0.00827 for 8 number of columns. For 8 number of columns, that multiplied by W, total weight on the girder, 3000 kilonewton, radius 2 meters, or it works out around 49.62 kilonewton meter is the negative bending moment at the support. And also the torsional bending moment coefficient is equal to 0.00063, that multiplied by WR. That for substituting which, now I'll get that torsional moment as 3.73 kilonewton meter, right? Then, and so now I'll calculate from this what is the total reaction on each column, because there are 8 number of columns. Hence, each column will get 3000 divided by 8, say 375 kilonewtons of the load on each of the column. Axial load in the column is 375 kilonewton. Then here, please see that here this beam or this girder is governed by the vertical loads, not by the bending moment, because compared to this 187 kilonewton, the bending moment is very small, 49. Even I'll show that, right? Now, hence, this is generally governed by the vertical loads and axial loads, right? Then, because those vertical loads are giving rise to axial loads, right? Some of the vertical loads will give rise to axial loads because of the complementary shear point of view, right? Then this area of the section required then from compression point of view, assuming the permissible axial compressive stress, assuming slenderness ratio lambda is equal to 0.6 Fy, substituting which I'll get permissible axial compressive stress as 165. If I divide 3000 10 to the power 3 kilonewtons with 165, I'll get around 18,182 mm square of the compression area required for the girder. Whereas if I calculate the section modulus from bending point of view, the section modulus required, ZXX required is equal to m divided by F. M is equal to 49.6 to 10 to the power 6 Newton mm divided by 165 permissible permissible bending or compressive stress 0.66 Fi 165, right? Now it works out say a value, very small value, 0.3 10 to the power 3 mm cube or 0.3 centimeter cube. It's very small, means this section modulus is very small compared to that of this area 18,182 mm square. Hence this indicates that the area in compression will govern rather than that of this bending criteria. Now let us try with a section area with 50% more for the trial section. Hence 1.5 multiplied by 18,182. Hence I shall try with an area approximately 27,000 mm square or 27,000 mm square or 27,000 centimeter square as appropriate, right? Now we'll propose a built-up section which consists of a web of built up with a plate 1000 mm deep and 12 mm thick web, and two flanges in compression and tension zone each of width 300 mm width, and its thickness is equal to 25 mm, right? The web is 1000 mm and its thickness is 12 mm, and the flange compression 300 mm 25 mm thick as shown in the figure, and which are welded so that it forms a welded plate girder as shown here, like this, right? Welded as shown here. This is a 1012 mm and 325 mm. This is welded plate girder, welded by fillet welds. That also will design at the end. That is how the cylindrical portion, vertical plate is stiffened by the horizontal stiffness, right? Like this, horizontal stiffness at every 1.5, 1.5, 1.5, and also they are provided by the stiffness running in the vertical direction also. These are also the same angles. ISA 65 by 65 by 6 running along the periphery of the vertical wall, right? Similarly, in the hopper bottom portion also, we do have the horizontal stiffness running at every equal interval of 1.5, 1.5, like this, and also in the perpendicular direction also, they are culminating at the apex point of the frustum of cone, like this, right? Therefore, that is how they are inclined. These are inclined, these are horizontal, right? Same size, ISA 65 by 65 by 6, both, right? And this entire setup of cylindrical portion along with this hopper bottom is supported on this girder, circular girder. This is a welded plate girder. Now you can calculate what is the area provided now. Hence I can check that the area provided is equal to 27,000 mm square. We're also looking for 27,000 mm square. Hence, okay, this is equal to 27,000 mm square. Therefore, okay. Now you can, because it's a symmetric I section, the neutral axis lies at the mid depth 500 plus 25, 525 from the top of this. Hence, YC is equal to YT, extreme fiber distance. Both are at 525. Hence, even the vertical axis lies at the mid width of this 300 mm, means at 150 mm from this end, right? That is how the CG is located. Once the CG is located, you can calculate the moment of inertia of this section, right? This now works out, say 493,984 10 to the power 4 mm to the power 4. And similarly, the moment of inertia about YY axis will now work out 11,250 centimeter to the power 4, centimeter to the power 4 or 10 to the power 4 mm to the power 4. And now I'll get, once I get this moment of inertia, I'll get the section modulus dividing this moment of inertia Ixx by extreme compression fiber distance YC is equal to 525. Doing which now I'll get ZXX section modulus about the major axis is equal to 9,404.23 10 to the power 3 mm cube or 9404.23 centimeter cube. And similarly, the section modulus about minor axis works out 250 10 to the power 3 mm cube. Then I'll calculate the radius of gyration, which is square root of Ixx divided by A. Doing which now I'll get the radius of gyration about XX axis is equal to 4.272 mm, whereas the radius of gyration about YY axis will now work out square root of Iyy divided by A. This works out, so 64.5, right? I'll what is that length between the two successive columns? I do have the total peripheral length pi d 4 multiplied by pi, which is between 8 number of columns. Therefore, the spacing between the each column is equal to 1.57. 1.57. Now, hence now I'll calculate the slenderness ratio. Slenderness ratio is nothing but this lambda is L divided by R min. Therefore, I do have this R min as Iyy actually. This is Rxx is 64.5. There's a typographical error here in writing, and Ryy is equal to 4.27. Therefore, doing which now I'll get the slenderness ratio. The slenderness ratio about slenderness ratio about major axis. About major axis Rxx. Actually, this is not Yy. Rxx is equal to this 64. Therefore, this length L 1570 divided by about major axis 64.5 approximately. This is 19.47. But from IS 800 1984, I'll note down for Fy is equal to 250. What are the permissible axial compressive stress sigma AC or FAC? For a slenderness ratio of 10, it is 150 MPa. For lambda is equal to 20, it is 148. Hence, now I'll interpolate for 19.47. It works out around 148.106 MPa, which is less than the permissible value, even assuming slenderness ratio lambda is equal to 0.6 Fy, which is 150. 0.6 multiplied by 250 is equal to 150. Hence, okay, right? Hence, now I'll calculate what is that actual axial compressive stress. Actual axial compressive stress is equal to total compressive force on the periphery of the girder, like this, periphery of the girder, right? Like this, right? The total, right? That divided by the area of this girder, 27,000 mm square, right? It now works out 111.11 MPa, Newton per mm square, which is less than the permissible axial compressive stress, 148.106 MPa. Hence, okay. Whereas I'll calculate now the actual bending compressive stress, which is M. M is equal to 49.62 10 to the power 6 Newton mm divided by Z. Z about the major axis of the bending is 9,404 approximately. Therefore, substituting it now, I'll get this result as 5.27 MPa, which is much less than the permissible bending compressive or tensile stress 0.66 into Fy 165 MPa. Hence, it is okay in bending criteria. But however, please make a note that this bending stress 5.27 actual value is much less than the actual compressive stress 148. Hence, it indicates that this beam is not primarily under bending action, but it is primarily under the compression action of huge intensity. Both are much less than the permissible values. Hence okay. Then next, now let us calculate the uh, uh, weld design, right? Hence the design of the weld. Then I'll calculate the intensity of the load per unit length. The total compressive force is equal to 3000 kilonewton, or that is distributed per unit length of pi multiplied by d. D is 4. So that works out the intensity of the compression as 238.74 Newton mm. Hence, if I assume a unit length of the weld, of the fillet weld between the flange and the web as 1 unit length, and assuming the effective throat thickness TT of that fillet weld as TT, then the permissible stress, axial stress or the shear stress in the weld, because now it will shear off, that weld will shear off due to the application of the compression force, that is FAW, allowable stress in the weld, as 110. Now I have the total load that is permitted on the weld per 1 unit length is equal to 110 multiplied by 1 unit length multiplied by TT, so many newtons. But what I can permit per this 1 unit length is equal to 238.74. Equating both of these, now I'll get effective throat thickness is equal to 2.17 mm. Therefore, this being a fillet weld, I do have effective throat thickness is equal to uh, uh, this S divided by root 2, S divided by root 2, size divided by root 2. Hence, the size is equal to root 2 multiplied by this effective throat thickness. Means 2.17 multiplied by 1.414. Say around some 3 point odd value, or let us say we may provide either 4 mm or 5 or 6 mm as appropriate. Hence, let us say provide a 6 mm continuous fillet weld for the connection of the web plate with that of the flange plate, a continuous fillet weld through and through in the compression zone as well as the tension zone. That is how the design of a uh, um, steel silo. Thank you, students, for watching this video. If you like this lecture or these discussions, please do click like, share, and subscribe to our YouTube channel. We'll meet with another topic in the next class. Till then, bye bye, students.